One of the interesting things about data centers is how they're loaded up over time. Data centers really are different than commercial buildings where in a data center there may be several weeks, several months even of very, very low equipment loads. So it's really important to understand how these affect energy use in the data center. One way to describe that in these two graphs that we're looking at is how PUE is affected by the IT load in the building. As an example, the top graph there is looking at the percent of the IT load as compared to, or what's driving the PUE. So when we have a very small IT load, the PUE goes extremely high. I mean, we've had customers come to us try to understand why their PUEs are so high after their facilities were just opened. And when you take a look at it, you understand that you have a lot of kind of base level loads that are running and consuming energy, but really no IT load. That bottom graph really demonstrates that, where we have in green there what we'll just call a baseline load, which could be lighting, it could be miscellaneous power, other elements of the data center that really don't have to do with IT equipment. And then over time, as the IT equipment comes online and increases, that green portion becomes a smaller and smaller portion of that total load, and that's really how we look at PUE. So it's a pretty simple idea, but one of the difficulties is people don't really have a good handle a lot of times on what will be that initial load in the data center, at least for the first few months or a few weeks. One way to combat that is modularity in data centers. Modularity is I think it's a pretty overused word. When we apply it to data centers, it's important to understand modularity is not just taking the load and spreading it out over UPS modules or chillers or air handling units. It's strategically developing a plan on how to build in this modularity to grow over time and give flexibility to how the IT systems grow. So as an example, one of our facilities in Sydney there is indirect evaporative cooling units, and they were installed in this way specifically to have this growth and modular approach to a data center as the facility expands over time. Similarly, when we look at the electrical systems on the UPS side, the idea behind this chart is not the exact topologies or exact equipment types, but rather to understand how different UPS systems work at different loading levels. Some of the equipment have a very flat load profile, meaning that at lower loads it's still fairly high efficiency, where some of the other ones really kind of take a dive after about 20 or 30% loading. And 20 or 10 or 30% might seem low, but actually when we're talking about systems with multiple redundancy 2N systems, those modules may never see more than 40% loading. So this is something to understand how the UPS system can have a big impact on energy efficiency. If we combine the thoughts of kind of reliability and efficiency and percent loading, we come up with these two charts. The top one really looks at the N+1 and 2N topologies in a UPS system. And what we're trying to demonstrate on this one is to take a look at, in a 2N system, we might have a little higher losses or lower efficiency over the span of the IT loading. But on the bottom graph, we start to see that the UPS load really is a factor of the reliability. So in the 2N system, as I mentioned, we may not have more than 50% of the maximum rated capacity of the UPS mods, just by the nature of the failover capacity. And all of these things will affect, based on the curve, which is in the previous slide, will affect the overall losses through the UPS modules. Going over to the cooling side, when we look at a chiller plant, we understand that each chiller will have a different loading curve, unloading curve, and will have different efficiency points throughout the span of cooling load. And when we build in redundancy and add multiple chillers, as an example, each one of the chillers, depending on the sequence, depending how it's run, may use a little more energy over the span of the different chiller types. And the more redundancies we put in, potentially the higher, what I'm calling here, energy or power multiplier will apply. So in the analysis of different chiller plant configurations, understanding how long or at what point the IT systems will run at will drive a design and drive what is the best energy strategy for that chiller plant. Kind of changing the topic a little bit and moving to the IT side, when we look at servers over the last 6 years, 5 or 6 years, we start to understand that their operating characteristics are different. This is data by Spec Power, which is basically a test that is run, industry standard testing that's run on different types of computer servers. And what we see, this is aggregate data over a number of different manufacturers' equipment. When we start to look at, say, 2007, the maximum full power, which is the reddish color bar there, versus the average idle power, which is the blue bar, you could see that in, say, 2007, they were fairly close, meaning as the computer was just having no workload, running its kind of normal background processes, we're consuming, more than 60% of the energy when it's at full workload. Fast forward to 2013, it's a dramatically different picture where the average idle load, is probably a quarter of what the maximum full load is. So this gives this kind of turn down in terms of what the server can do in relation to the amount of energy it uses at a low P state, low power state, versus its full capacity. But one other thing off this graph that's worth mentioning is you can see where the maximum full power is headed. So even though we have a less, in terms of lower power state, average idle power state, the maximum power state is increasing. And so this is something that interesting, so it's kind of mixed results in terms of we're saving energy on one end, but as we get to more powerful servers, they're consuming more energy. Modularity, we tend to talk about that mostly on the power and cooling side, but one of the things that we can't forget about is that on the IT side, there's a sense of kind of modularity. As an example, this server, it's termed a software-based server, is made up of multiple small kind of cartridge servers. And each one of these servers will be driven off of whatever application it's meant to take care of. If the application's not running, it's either at 0 or very low P state. So what we end up here is this server has basically 45 different levels of discrete power consumption or energy over the course of time. And this is a different level of modularity we can look at in the IT systems. And this is what I referred to back in my very first slide, this kind of convergence of when we start to understand how the IT systems can work with the power and cooling systems to make sure that we're kind of meeting the equal energy efficiency goals. Okay, the last slide I want to talk about is kind of a summary of a number of different topics. This is a project that we just worked on a few months back, and the idea here was to develop a kind of worst case and best case PUE. So I'm kind of going back to PUE now and looking at what are some of the ways that we can predict or understand energy consumption. So in this case, we looked at a high energy use state, looking at Singapore as a location, and then some other parameters that are, say, less energy efficient. And then the low power state really is good climactic location, Helsinki, different economization, energy efficiency strategies, etc. And when we map those out and do energy analyses, we see that these different types of data centers have different types of ranges of PUE. So it's kind of a mix of data center type and cooling system type. The idea here is that some of the data centers or some of the cooling systems that have very low PUEs might have a very high PUE at the high end when the worst case scenarios is put in play. Whereas like the container, the third bar down, the container with adiabatic cooling, just by the nature of how that works, it can be applied really with a very small range of PUEs. So each one of these has its own characteristics, and certainly every one of these cases, has parameters that can be changed and modified and improved. But the idea here is when we start to look at a data center strategy, overall PUE, overall energy consumption, and looking at different types of cooling systems, understanding the range of energy consumption and PUE will really help us out as we build our roadmap to developing this ultra-efficient optimization within data centers.